All right, so this is Chapter 3, Acids and Bases. Like I said, that first slide was the homework. So you guys remember Bronsted-Lowry acid-base theory? Of course. Right. Proton donor, proton acceptor. So, in general, right, your proton donor has a proton. Right? When we say proton, what do we mean? Hydrogen. And it's H plus because otherwise it would be a proton and an electron, but the nucleus for a hydrogen is a proton. So it's been for years just called proton donor, proton acceptor. Okay, so the donor does what? Donates. It donuts. Okay, the way we did this in Chem 1B, we would say, oh, the hydrogen does that, right? And then you end up with the chloride. The chloride because the hydrogen left, just the hydrogen, just the proton. And you end up with this hydronium ion. Right? And this is an equilibrium process. This part that's here. Okay. And for our equilibrium processes, we can write Kas. All right. Now, for Kas, just a little side note, big Kas are strong or weak? Strong. Do you remember pKas? No. So big Kas are strong. Let me write this little note. And then we have pKa, which is just like pH, negative log of Ka. So lower pKas, because of that negative sign, lower pKas are stronger. Acids that we deal with in organic chemistry are typically often, typically, pKas can be as low as -9. So that would be like 10 to the 9th. Those are huge equilibrium constants. Okay. We'll talk about a little bit why we don't distinguish between, like when I say sulfuric acid and perchloric acid or hydrochloric acid, what kind of acids are those?
Oxy.
No, hydrochloric's not oxy. Strong acids, right? We classify them all as strong. And we learn this from just memorizing lists of strong acids and strong bases, right? And then we learn like trends, like how do we tell if it's a strong acid or a stronger acid? And we look at like number of oxygens and all that stuff. And we're going to do the same thing here, okay? But in organic chemistry, we actually measure how much stronger each one of those acids is, right? But we can't do that in Gen Chem because we do it on water. And I'll explain that to you. But if you want to look it up ahead of time, it's called the leveling effect, which basically says all strong acids are as strong as hydronium. And that's the strongest acid you can have in water. Okay, so then we end up with acid-base, and then we have conjugate acid-base pairs. So this is HCl in this one is doing the donating. This is from the last one. So this is my acid. The water is the base. It's doing the receiving, right? And chlorine would be the conjugate base, and hydronium is the conjugate acid. Because when we're talking about the equilibrium concept, the reactions are reversible. So that means in the reverse, the proton is going to go from the acid, the conjugate acid, back to the base to establish the equilibrium. Okay? So we have a forward reaction and a reverse reaction. Conjugate just simply means on the reverse reaction, it's acting as either the acid or base. Okay, so that's on the bottom one. Let's label acids and bases real quick. That's T-butoxide, by the way. That's the name of that ion. This guy here. T. If you drew the Lewis structure, like that, you can see why it's called T. It's butyl. Butyl means 4. That says 4 carbons in it. So T-butoxide ion. So which one's the acid? Which one's the base of this pair here? This is the acid. T-butoxide ion is the base, then. Has to be. How did you make that determination?
Because the H left the water.
Yeah, because it's in red. Because, yeah, the H goes from here to here during the process, which means this is the acid. You know that because when you look over here, you have hydroxide. Okay? So this is the conjugate acid, and this is the conjugate base. Okay? And they're pairs, so the base always gives rise to the conjugate acid, and the acid always gives rise to the conjugate base. Okay, so let's draw some reasonable products for these reactions. And they tell us which one's the acid and which one's the base. Later, you're just going to have to figure out which one's the acid and which one's the base. It's not that bad. You'll know. Some of it's just intuitive. Okay, since the water is the acid, what is it going to do? It's going to donate, right? Oops, sorry. So this will donate. So one of these will go over to there, right? And then you'll end up with like that. And a positive charge. This is an ammonium ion. It's not ammonium, but it's an ammonium-like ion. Nitrogen with a positive charge. Just a little side note, if it ends in IUM, it's usually the positive ion. And the other one is hydroxide. Can't see the dots. Let me just draw them. Let me draw them as lines. And I'll circle the charge so it doesn't get too confusing. Okay, now let's do the bottom one. Now, look, it's the same thing, right? But we switched which one's the acid and which one's the base. Oh, I'm sorry. I left the H's off of it. Oh, I already... No, there are CH3 groups. So it's a bond line drawing of a combination of a bond line drawing with dots. Oh, it's not ammonium, it's an ammonium-like ion. But if it ends in IUM, it's just a positive ion of nitrogen.
Wait, that's not ammonium?
Ammonium, they would all be hydrogen.
Oh, I didn't realize. Ammonium-like.
It's actually, because it has two methyl groups on it, its name is actually dimethyl ammonium ion. So, but I just got rid of the dimethyl because I wasn't so worried about that right now. But it's an ammonium ion. Anyways, so if the nitrogen's the acid, if the amine is a acid, the nitrogen-containing molecule is the acid, what happens?
That one.
It loses the hydrogen. Oops, sorry. And then it's left with two lone pairs. It'll have a negative charge because of that. And the water will be left as a hydronium, like that. Okay.
Why would nitrogen have a negative charge?
Because, well, you can just count the electrons, for one. But remember, in an acid base, in like Bronsted-Lowry acid base, you just take the hydrogen's proton, not the pair of electrons that make the bond. You just take the hydrogen off and you stick it onto something else. So if you take the hydrogen, like here, it's sharing this pair of electrons, right? But if you just pop the hydrogen off without taking the electron, the hydrogen's going to have a positive charge. It's going to leave the negative charge behind, the electron behind. Okay, so water is considered neutral. Does this mean that it's neither an acid or base? And the answer is, you guys know the answer? It's both, right? It's amphoteric or amphiprotic. Yeah. That word is amphoteric. It acts as both an acid and a base, depending on the situation. Like if it's with something that's a stronger acid than itself, it will behave as the base. If it's something with such a stronger base than itself, it'll act as the acid. Okay, so now we're going to use curved arrows. Go figure. And we're going to just screw up everything you ever learned about drawing electron arrows in chemical reactions. Okay. So, bonds break and form when pairs of electrons move. So we're going to use the two-headed arrow. Remember I talked about one-headed arrows, two-headed arrow? We're going to use the two-headed arrow. And let's say, Connor,
Yes.
You're an acid. Okay?
I'm ready.
This is your proton. I am the base. So this is my pair of electrons. Okay? Watch this. Very technical. To get the proton, I have to take it away from him.
Yeah.
Right? But if I don't take it from him,
Will I give it away?
he won't give it to me because I'm not taking it. See, that's the important part. It's the pair of electrons that takes it, and then he lets go of it. The hydrogen never just says, I'm leaving, I've had enough. Right? That would be if he took the eraser and he threw it at me. It turns out acids and bases are much more civilized than people are.
They'll only go up there after.
They will only leave if they're asked to leave by another pair of electrons. So let me get that.
All right. I'll give it to you.
See? How civilized. So, yeah, so if you look at this drawing then, that's what this means. And every proton transfer reaction, I'm going to write that at the top because I love saying proton transfer reaction. Involves two arrows. The base, and this is still the Bronsted-Lowry base, is going to bring the pair of electrons, that's my hand, to grab the proton, and then the acid will just let go of it. So the base brings its pair of electrons in, like this, and then the acid pulls his electrons back, and that's the proton transfer. The reverse, it's an equilibrium process, right? So the reverse is also true. When the base, the conjugate base, which is A minus over here, decides it wants the proton back, it takes an arrow of electrons. Remember, that's two electrons, like that. They don't have a fight over it. He just gives it up. Like that. Again, two arrows, one's grabbing for it and the other one's letting go. What determines how strong an acid is the relative strengths to which one grabs and lets go. Okay? If this was a much stronger base than this was, then this one would be grabbing a lot faster and making the reaction favor the product side.
Strong acid, weak base, and it's holding on stronger than it. No. Weak acid, weak base, it's holding on stronger maybe, and not able to give. It's not. The other ones aren't taking away.
Right. Yeah, you're making it more complicated though, because what we usually do. So, like, if I wanted to know, because you're talking about the relative strengths of the acids and the bases, what we usually do is we compare either the acids to each other or the bases to each other. Because that saying that we learned in Chem 1A, the stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base, those are still true. So if you compare the strengths of the acids, that's the same as comparing the strengths of the bases, but you're just looking at the acids instead of the bases. Make sense? No? Okay. I'll try to clear that up as I go along, because there's a lot of this. So this curved arrow business, okay, shows us how the reaction takes place. It's not this magic proton floating around. It's the actual exchange caused by a lone pair of electrons on one species to grab the hydrogen in the breaking of another bond, and that's called the reaction mechanism. It says down here, learning to draw mechanisms is one of the most valuable skills in this class. You know what the other most valuable skill in this class is? Study skills. Because there's a lot of mechanism drawing, and the only way you're going to learn them is by just doing them over and over again and studying like why they happen. It's a great class, though. I really like this. My favorite. I think I said that about 1B too, right? It's my favorite class. Did I ever say that?
You said OChem.
Did I say OChem was my favorite and 1B even? Okay. Yeah, I like the... Yeah, anyways. So the base... See, I'm more civilized. The way organic chemists actually say it is, they say the base attacks the acid. Oh, shoots, I keep pushing on things. Spit on my screen. But you could say that this is the attack. And then the acid lets go right here to form the conjugate acid and conjugate base. So it says, remember I said 2 arrows at a time? It says the acid cannot lose its proton without the base taking it. Okay? We say that that process is concerted. So they both happen at the same time. You can't have one arrow and then the other. Good? Let's draw the arrows going the other way. What would the arrow going the other way look like? Well, first of all, just so you see this, okay? If I want to draw the arrows going the other way, this is not a suitable drawing. You actually have to, because you're going to have to break a bond, you have to draw the bond. Remember I talked about sometimes when you draw Lewis structures, you draw a bond, and sometimes you don't. Depends on the purpose of the drawing. The purpose, what I'm going to do now, is show how the reaction operates in reverse. Yes, I know water is not linear. That's all the space I have. But there's a water molecule like that, okay? And then, again, a pair of electrons from the conjugate base will attack a hydrogen. Which pair of electrons doesn't matter. And then this one has to release. Like that. Not much room there. But that gives us the reverse arrow of the equilibrium reaction. Okay, so let's draw the curved arrows on this guy. We know which one's the base and which one's the acid. So we're going to use arrows just like we did in resonance. And where do arrows always start from? Arrows always start on electrons. So on this nitrogen, this is the base. The base is going to attack or come with its pair of electrons. And it's going to attach themselves, they're going to attach to a hydrogen. Now, you know, it doesn't matter, like, if you do this. But you probably won't want to do that. Just try to take the closest route. Don't try to copy that, but I'm just going to erase it right now. Just go like this. And so what's happening here is I am starting on a lone pair. Most acid-base reactions start on a lone pair. Or can start on a lone pair. Sometimes they show a pi bond moving, but it's still a pair of electrons. But most of the time, it comes from a lone pair. It goes to the hydrogen, and then what has to happen to the electrons on the hydrogen-oxygen bond? They have to go back to the oxygen. And this is the very civilized letting go of process. My arrow is not very good on the left arrow there. It should be going right at the hydrogen. I just realized that. It should be like pointed straight at it. And then these start on the bond. And go to the atom. And the nitrogen lone pair starts on the lone pair and goes directly to the hydrogen. Right. And I better work on my handwriting. That's all it says there. I got a little excited. I'll slow down. Okay, let's identify acid-base steps in this reaction. So this is a reaction mechanism. It's called a E1 elimination or dehydration reaction. It doesn't matter. We're going to spot the acid-base steps. Okay? So an acid-base reaction is the attack of a lone pair to a hydrogen. That's the first thing to recognize, right? So where do you see lone pairs to hydrogens? First part, right? Yeah, this part here, this is an acid-base. Oops, I did it again. This is an acid-base step. Oops, gosh darn it. Having a pen control issues here. That's an acid-base step here. This second step, so this is one step in the reaction mechanism. This is known as an intermediate. You learned about intermediates in Chem 1B. They're partway through the reaction towards the product. This is not an acid-base step, right? It's just breaking a bond. There's no attacking of a hydrogen by a lone pair. This is actually known as loss of a leaving group. We'll learn these terms later. And then after this arrow, you end up with this. Now you notice what happened. I pulled the electrons away to the oxygen, so that's why I have a carbocation here now. And what kind of step is this?
Is that like the reverse version of that, how the lone pair went to the H and then...
Kind of is. Kind of is. It's the protonation of the water to form the hydronium. Turns out hydronium is a catalyst in this reaction. So you'll see it. It gets used up here in this step, and then it's reformed in this step. But this is also an acid-base step.
Yeah, it is.
So those two steps that are circled are acid-base, and the thing in the middle is called the loss of the leaving group. From here. So really quickly summarizing the arrows, okay. Start on a lone pair, and you go to an atom. Now, in an acid-base reaction, the atom is a hydrogen, okay? And when you do that, you form a bond. Oops, sorry. We also learned from resonance that you can move arrows from pi bonds to sigma bonds, and that's really a pi bond moving, so that's resonance arrows, right? You can do that. You can also break a sigma bond. We showed one example about that. That's not a resonance, but it's like the hydrogen when you break the sigma bond between the hydrogen and an oxygen, for example, right? In an acid-base reaction, that bond breaks and it forms a lone pair. So just to really quickly illustrate some of these, right? You can have in water, for example, the self-ionization reaction, pair of electrons like that, pair of electrons like that. This is, let me do this real quick. A, B, and C. This is A, and this is C.
So before we couldn't start from a single bond, right?
For resonance, because when you move a sigma bond, you change the skeleton. And remember, in resonance structures, you can't change skeletons. But you can use a pair of electrons to do that. Okay.
Now we're showing reactions, so we can break sigma.
Yeah, so we're looking at reactions, so sigma bonds are broken all the time. By definition, have to be. What is that smell? Sorry, I think it's fish. You can also have things like that. That's a case of B, a pi bond moving to a sigma bond. And just remember for charges that when you lose an electron, your charge becomes positive. So if the arrow moves away from you, your charge becomes positive because you're either sharing or losing electrons. And if the arrow is coming towards you, your charge becomes more negative. Okay? Oh, sorry. Pretend you're an atom on a structure. And you're looking at an atom and you're saying, that's me. And then the arrow's coming at me, so you're getting more electrons. Your charge will be more negative. It's not like you're in class and I'm throwing arrows at you and you're going to be like, oh, my charge is negative, so you throw arrows at me and your charge becomes more positive. I don't know. Anyways. And then, and the last thing to remember is in all these things, when we move electrons around, charge is conserved. So you never like have a net change in charge from reactants to product side unless you actually specifically, in redox reactions, you specifically write the electrons out to show how the charge changes, okay? All right. We'll get to this next time.